Hello, 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 Isabella. Hello,
Oh,
Queen. Hello, awesome. Hello, Kaylee. Hello, Aaliyah. Hello, Rachel. Hello, Amanda. Hello, Arlene. Even our iPhone. Hello, Farina. Hello. Oh, that was weird. Hello, okay, that was cool. Hello. Did I say Amanda? I said it. Rachel. Amanda, Rachel. Hello, hello. Okay, I think that hello. Good afternoon. Did I say that? Yes. Okay. Um, okay. Um, um, okay. We're going to get rolling even faster today, I think. Well, in a way, we're going to get rolling fast. All right. I want to get straight to business, although today's been a very crazy day already. In the other class. So I having major internet issues today, which is always fun and interesting. So the board is coming in and out. I'm hoping that the board is coming back to us in a moment. Um, One thing I will say, I think it definitely is now definitely time for people to do the math methods sheet. It looks, I think, yeah, let's start on that math method sheet. I would like to start. I might be confused, but I feel like very few of those have come in yet. So let's start. It's not too late. Definitely not too late. Starting to be let's just get going on that. Okay. But I want to keep going with exactly the material where we were 2 days ago. I'm slightly stalling because of this board situation, but yeah, I want to get up back to exactly where we were 2 days ago and just, you know, we're still kind of like setting a table and not really eating yet with them, not because of us, but because the nature of the math, like there's a lot of this building. So I want to get to the action. Oh, I could be, oh, thank you. Oh, cool. That might, hold on 1 second. Sorry, I'm just, okay. Just a quick response on the private chat. Okay. We're gonna start in the middle. Yeah, I think I can make this work. But so again, just where I am in my head is that there's nothing major going on in the class. Like most of you want to be doing math methods. And I really think by the end of today, by the way, I mean, um, if you ever did look at it and it looked intimidating or something, I think today will help a lot. I hope. Um, and what today is exactly. Maybe this. Okay, what this is exactly picking up where we were on. Good heavens to Betsy, where we were on Wednesday. Okay, this is the thing that's about to work on, which is where I think we were from Wednesday. Is it in my mind? Physics gave us a second order differential equation, like physics data or laws of physics presented us with a situation where instead of knowing x as a function of t, which is what we always ultimately want in physics. Here we go. I think. Okay, I think this is working. So bear with me. I'm sorry, but this is and at least one person in direct messaging has already very nicely volunteered to help out with this board situation if this doesn't work. But bear with me for a minute because I think maybe it will work. Um, Yikers Island. Yikers. Oh yeah. Okay. 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 While I'm crossing my fingers, but have I mentioned Gus Johnson? If you're ever really bored, there's a YouTuber named Gus Johnson that my older son used to watch a lot. He's like funny. I mean, he's supposed to be funny, and he is funny, I think. And he does this one satire, like this one YouTube thing called "How to Be a Professor," and he's totally making fun of professors, obviously, and particularly he's making fun of professors when professors try to manage technology in front of classes, like try to put something up on the screen. And it's really embarrassing to be a professor while watching this thing that Gus Johnson does because it is so accurate. And I thought, okay, wait, okay, we are almost there. But it's even more embarrassing to be a physics professor in front of technology because, like, you'd think I would maybe have a relationship with technology, and you'd be right. But my relationship with technology is much like many of my relationships. It's a great place to visit, but I wouldn't want to live there. All right, hold on a second, or something like that. Um, we're coming. We're coming. You're okay. This must be watching somebody else watch their own pot boil must be so interesting. Okay, wait. I'm gonna while this thing thinks that it's connecting. Lord, while this thing. Excuse me for a second. I may give up in a minute, but it thinks it's. Oh, yes, it thinks it's finding me. Oh, yes, it feels connected to me now. Our relationship is improving already. I think it's going to buy me an Easter present. I think I want to tell it that I'm Jewish. Okay, here we go. I'm hoping for Easter actually that Siri buys Mrs. Google. Okay, here we go. Okay, thank you for your patience. And all this class may fail at any, I mean, it always might be, but we might, all right, here we go. I apologize, but yeah, our whole internet in the house right now is, um, is dangling by a thread. I suppose it really is a web. It's like a spider. It's like Charlotte's web. Okay. Here we are. Sorry. So I'm going to quickly just say where we are is right. Okay. To quickly review, and sorry, and you really can stop and ask questions. Of course, I know just because I'm not saying anything interesting does not mean that you can't. I'm saying though now, here's where we are as of last Wednesday. Like the big black equation on the top, is again an equation that physics like had us stumble upon. Like we didn't look for that equation. It's not the simplest math equation in the world. It does describe what's going on. So we're like, oh, we need to solve that. But solve it means get x as a function of t. If you name the time, we name the space. That's always our job as physicists, right? So what we did, I mean, you guys and me, last week, used a bunch of speculation and extrapolation and data picturation. It's not a word. And we conjectured that the function x equals x naught cosine omega t was a proper equation of motion to describe an oscillator. Right now, again, what we're guessing, and of course it turns out to be right. I mean, it is right. Otherwise, I wouldn't be spending so much time on it. But I also just don't want to just tell you that it is right and move on because you have no reason to believe it and blah, blah, blah. But what it is, this x equals x naught cosine omega t thing that we conjectured, it's like our modern day equivalent to x equals 1/2 at squared plus v naught t. Like it is our now equation of motion, like the rule that we would use to make predictions about an oscillating system. Like 1/2 at squared is what you use for like a free falling system or some kind of constant acceleration. But this is what you use if you don't have constant acceleration, if you have constant oscillation, like patterned back and forth. We're predicting that if you want a rule that tells you for all times, you name the time, we'll tell you where the oscillator is. If you want such a rule, we're guessing that it is, okay, x equals x naught cosine omega t, where x naught means the very first place that this object ever is. And we're saying that's our guess. And we're saying we don't really know how to get omega. We're just guessing omega would have to be there because something that's measured in radians per second would have to be there, like be in the equation. Like literally, and again, we're trying to be real here. We guessed that there'd have to be something with radians per second right next to the t. We called it omega. It's all we know about it so far, or anything that we could picture that radians per second might mean. And we're like, this is our guess. We think this is the rule that you would use if you, from now on, if you're ever faced with a mass on a spring, like use this, and you'll be able to predict for any time you name where the spring is. So if we brought this to a person, like another physicist who's or whatever, and said, here's our conjectured equation of motion for an oscillator, what that person would very reasonably say, like a physicist or mathematician or whatever, just anybody who's been paying attention this whole time, would say two things. One, okay, I'm glad that's your conjecture, but how do you actually know it's true? Like you gave some good reasons, but you never proved that that was true. And then they would also maybe say, well, even if I believe you and I want to use that rule from now on to track oscillators, what do you mean by omega? Like that, like even if it means radians per second, like how am I going to plug into this thing? I don't have omega. Even if you tell me the mass and you tell me the spring stiffness, what the heck do you mean by omega? So what am I supposed to plug in, right? So that's why. So, and this all with any differential equation, in the attempt to solve a differential equation, one always has a conjecture, but then one always has this twofold dilemma. One has to verify that the conjecture is right. One also needs to know what the heck they mean by those constants in it. Otherwise, it's useless. We do know what we mean by x naught. We already defined that. We mean x at t equals 0, but we don't know what we mean by omega. Like we don't know, have numbers for it. So what we did, okay, and again, this is technically a review, but so we did what we should always do if we ever have a differential equation, and this isn't the last one. We differentiated our guess. Now I'm going to add, well, no, I guess we did do this last time, so I'm not going to put you through, but we differentiate our guess, in this case, two times, because we have a second, or because, because the kind of derivative that we are being told about is a second derivative, right? So we're going to differentiate this thing two times. And first of all, find out whether it does meet the form that we want. And second of all, find out what the heck we mean by that omega. How can we express it in terms of what is measured and known in the lab, i.e. spring stiffness and mass. So what we did, now this part, I'm not going to put you through. I mean, I think some people still need work with this, and you should quietly make a note if you do need more work with this, but I think we did this one, so I'm going to, oh, sorry, someone's here. But we took that expression, our conjecture, the x of t expression up here on the top. We took its first derivative. We used chain rule and trigonometric differentiation. So we got dx dt equals, or we're getting, I'm either reminding you or I'm telling you, dx over dt equals negative omega x naught sine omega t, right? Like I brought the omega out from chain rule and I put it next to the x naught, like because the x naught was just sitting there the whole time. But I got a negative sine and sine because the derivative of cosine is negative sine, right? So, and please stop me, even in the private chat, literally in the private chat, if you want to admit that you didn't follow the sine part of the chain rule, don't be, even if I can't fully help you now, I still won't criticize you. If you, whoever you are, if you don't get this calculus, it's not too late to tell me. Even if it is too late, it's not too late. But anyway, then we took a second derivative. Again, why? Because I'm like looking to relate back to my original second order differential equation. So I took the second derivative. Well, chain rule brings the omega out again. But now the derivative of negative sine is simply negative cosine. Like the derivative of sine is cosine. We don't change the SIGN of it. So same thing, the derivative of negative sine is negative cosine. So the negative sign stays in my life here, but one more omega comes out from chain rule. So I have that the second derivative is negative omega squared x naught cosine omega t. Now, and I know I did this already. And again, even if you already did follow it, please, I apologize. But one of the next steps here is the one that's really easy to forget if you don't do it over and over in practice. The step coming up. Like, remember, what we just got, what I got by differentiating twice is this. Like, if I took that expression that had an omega in it and I differentiate twice, I get this. I still don't know what the frick I mean by omega. I just know that it is a constant that's measured in radians per second, and now it seems to be like squared. in this expression. But remember that what I wanted, what I was given originally from physics was d2x over dt squared equals negative k over mx, like something incredibly similar, really similar, but not identical. So let's be careful. Like what I wanted to solve, what I was trying to solve is this thing. And remember, and these are actual numbers from the lab, but a number divided by a number is simply a number, and a number that's not going to change. So what I knew is I was looking for some x such that when I differentiate it twice, I get back itself times some kind of positive constant times a negative sign, right? Like I could compact this whole thing and just say times a negative constant, but we're just trying to be careful and clear. So this whole equation says we're looking for an x such that when you differentiate it twice, when you take a derivative of it and you take a derivative of it again, you get back itself, but times some kind of constant times a negative sign. That's what the differential equation was saying. Now, first of all, it's not a coincidence that we thought of cosine. Like even if you didn't follow anything about the graphs or the lab data or anything, if you remember from calculus, cosine is precisely that type of function that we're looking for. The type of function which, when you differentiate it twice, you get back to itself, but times a constant times a negative sign. The constant in the pure case happens to be 1, but I'm saying like what's the derivative of, I'm being rhetorical for a moment, but remember, the derivative of cosine of x is negative sine of x. Then the derivative of negative sine of x is negative cosine of x. So that means when I took two derivatives, I got back to cosine of x, but times 1, which is a constant, times negative sine. Like that's already good. Like that's why cosine is doing for us what we're looking. But specifically here, it looked like when we multiplied our tested out function, when we differentiated it twice, what we got back itself times this constant times a negative sign. So we did get something when we differentiated twice, we got back itself, we got it multiplied by a constant and multiplied by a negative sign, which is exactly what we were wanting. We were wanting something that when it got differentiated twice, it would be itself times a constant times a negative sign. And the only odd or concerning or like moment to pause is that it looks like they're not the same constant. That's the thing. Like that's what I want to be clear about. Like in the original form of the question of the differential equation, the constant is k over m. These things that we know about the spring system, stiffness and mass. But in the solution that we just got, or in the check that we just got, the constant is called omega squared. It's called something else. It's not like a ratio of 2 letters. It's 1 letter and it's squared, right? So we have to take note of that. But what we say to ourselves is, oh, wait a minute now. They're both constant. Omega squared was the name for some constant about which we knew very little. We just knew it was a constant and it had to be measured in radians per second. K over m, we knew was a constant. And we knew exactly it was one constant divided by another. So there's actually no contradiction between this omega squared name and this k over m name. It's two different names that refer to two different things that we seem to know. If they're in contradiction, then this doesn't work. But if they're consistent with each other, then not only does this work, but we've learned something. In other words, what I'm saying is this solution, this is what it says now here in the blue, what we're saying from this important step of verification, we're actually saying that when we differentiated twice, we learned two things. One, that the cosine solution does work. It is a good way to describe and predict an oscillator. But 2, it works if and only if, like IFF, if and only if it works specifically as long as omega squared means the same thing, refers to the same numbers as k over m. If k over m is just one name, stiffness over mass, and omega squared is some other name like radians squared per second squared, as long as they are one and the same, in other words, as long as the rate at which this cosine function oscillates back and forth, as long as the number of radians per second that is covered by this cosine function. Now, again, I still don't know what that means physically, but I'm just saying the one thing I know about omega is it's supposed to be some rate measured in not a rate of velocity, not speed, right? But a rate of radians per second. Now, again, I don't even know in my brain, if I hear radians per second, it's not obvious or easy right away to picture what that means or what it has to do with our spring. And I'm not asking you to just yet. But I'm just saying if the only thing we know about omega is it's some kind of rate of radians per second, like maybe you could picture on a cosine graph, like maybe it's like the number of humps per unit on the x-axis or something like that. But whatever it is, we're saying that that rate is fully determined by the constant features k and m. Like we're saying that this cosine description of oscillation works and guarantees that the oscillation goes back and forth at some sort of steady cycling rate. And specifically what we're saying is that cycling rate seems to be entirely determined by the square root of k over m. That like this whole cosine idea works as long as by omega, what we mean is the square root of k over m. And I know we said this on Wednesday, and this of course means that you can then plug in numbers for question 9 from homework 1. But I want to, but now I really want to probe this. If this is what we're saying, so okay, so very, very concretely, the finding here is, I want to make this as, I tend to not make this as concrete. So I'm saying, and I will write this again. I don't know if that's even legible at all on the side there. What I'm saying is the concrete finding for the moment, the concrete discovery, whatever it is, if you have a mass m on a spring k, and you let the mass go from anywhere other than equilibrium, it will go back and forth, back and forth, back and forth at a steady rate. And that steady rate, and it'll go back and forth in a steady predictable rate that you can predict using a cosine function. And the steady rate at which it will do that back and forth, which we can measure, you're going to see in radians per second, that steady rate is entirely determined, is equal to square root of k over m. The number of radians per second that is undergone will be entirely determined by the stiffness of the spring and the heaviness of the mass. That's what we're saying so far. Let me go on for a minute. Now, what is this radians per second business? Like, so I'm saying omega, is a rate that we're going to call angular frequency. Like, we're not going to call it velocity because it's not a velocity. It's not amount of space per time. Like omega is not measuring how far you go in time. It's measuring something else in time. It's measuring radians. Now, what the heck are radians? Like, why are radians? I mean, we know why because of cosine, but why are cosines and radians? This is a rhetorical question. I'm not actually asking anybody, but like, it is worth stopping that all of a sudden we've got this omega thing here that I'm saying omega is equal to square root of k over m for all time now. Like you could memorize that, but you got to understand where it's coming from here. We're saying whenever you have a k and you have an m in this way, you'll get an omega. That is definitely the square root of k over m. That omega is measuring radians per second. But what the heck does that mean? Why are there radians if you just have a mass that's going back and forth horizontally? Like, where are radians coming into play? Here's where. A radian is a fraction of a circle. In fact, let me be even more specific. An angle, it is a portion of a circle. It's easy to think of angles as like intersections between two lines or two line segments or something. Like it's easy to think of an angle as like two arrows meeting at a point, making like a V, and the angle is like how thin or wide the V is. Now, I'm not saying that's not true, and that's often how I picture angles. but it's actually a very confusing way to picture angles. Like it doesn't actually help you remember what an angle, like an angle is, yeah, like the space between my two hands of this V. Sure, like this V, like forming some sort of angle, and this is a bigger angle. Like I think we're all clear on that. But what is it exactly we're measuring when we say that? When we say this is a bigger angle than that, or if better, I say like, oh, everybody can recognize. Sorry, everybody. Whoa, I'm a spaz. Look, we didn't know that. Okay, everybody can recognize that here's a right angle, right? Like what you might call 90 degrees, or I might call pi over 2 radians. But I'm going to say right now, I don't care what we call it. Everybody could pretty much, or you can either recognize a right angle, or you could say Yaverbaum. That is totally not a right angle, you spaz. Point being that you know what a right angle is. Now, what is it? It's not some specific distance between my two hands. Like I know my hands are wider apart now than they are now. So at some level, it seems like, oh, bigger angle means like greater distance between the two lines. But let's be clear, like it's not a distance, because if you were to draw the distance between my two hands, like as a straight line or something, like straight across, well, first of all, then that's just distance. And it has nothing to do with my hands. You're just measuring a distance between a point on my hand and another point. Second of all, as you all know, how far apart are my two hands? Well, it depends whether you measure over here at my palms or you measure way out there at my fingertips. Like the angle that you're seeing right here is not how far apart my two hands are. I wouldn't even know how to measure that. It's how far apart they are, like along the arc of a circle, right? It's like how much my hands have opened up sort of in this curvy way that they open up in other words, when you say that this is a right angle, if you really think about it, and this is really true what I'm about to say, it makes life much easier for me, but it's like true. It's not a trick. When we think of angles, we should think of them the way the Greeks did. Don't forget numbers. Forget whether this is 90 degrees or pi over 2 anythings. What this is, this right angle that I'm spastically trying to do, this right angle, what it is, why it's recognizable, no matter how big my hands are or where you're even looking at this. Even my hands get cut off, you know what angle this is? Because what it is a fourth of a circle, right? That's what a right angle is a fourth. And I want to say this resoundingly, because people go through entire math programs and never know what an angle is. And that's why they can't do trigonometry, because it's all about freaking angles and no one ever. What an angle is a portion of a circle. Like think sports or like snowboarding or skateboarding stuff. Everybody knows what a 360 is, right? Now it's like, it turns out to be kind of dumb that we call it, like degrees are kind of dumb, but it doesn't matter. We all know a 360 is a full circle, and everybody can recognize a full circle. And it doesn't matter how big the body is of the person doing it or how big the radius of the circle is. Like, you know, a full circle when you see it. And you know that if someone only goes a half a circle, we call that 180, right? And 90 is a fourth of a circle, regardless of how big the circle is or where you cut it. But so what it really is how much arc length you get per radius of circle, right? That's what I'm trying to write on the board here is, if you really think about it, an angle is a pure fraction. Like it's the number of meters in some arc length, like how long some arc length on the perimeter of a circle is, divided by how big that circle is, just to acknowledge the fact, right? Like really what an angle is in effect is arc length. Like if you cut out a fourth of the circle, if you cut out a fourth of the arc length of a circle, you've cut out a fourth of the circle. That's 90 degrees. But what I'm saying is, we all know that one easy way, if you want more, if we both have pizza and you want more crust, then if you want a lot of crust, you could either take a much bigger slice out of our pizza, or you could take the same size slice. You could just take a fourth, God, I can't speak. Say we have a pizza, we divide it into 8 slices, right? I give myself a slice, I give you a slice. Okay, we both now have 2 even slices, 2/8 of the pizza. You suddenly decide that you want a lot more. You're like a crust guy. You're like all into crust, and you want as much crust as possible. Well, what you could do, of course, is take a bigger slice from. You could take 2 slices and put them together. Now you have a lot of crust. Or you could take the same size slice out of a much bigger pizza, and that would give you more crust as well, right? Like if you took if you took a pizza and also divided it into 8 slices, but that pizza had twice as big a radius as ours, I'm making much bigger deal of this than I should. But I think you can all picture, if you go way out on a bigger pizza, you're going to get, if it's literally twice as big a pizza, you'll literally get twice as much crust for any fourth or any eighth or any 16th that you pick. In other words, an angle is just amount of crust length measured in meters divided by radius measured in meters. So the meters cancel. So whatever an angle is, even before you get involved in degrees or radians or anything else, an angle is a pure ratio with no units. It's a fraction. It's a decimal. It's a fraction. An angle is just how big a fraction of a circle are we talking about here. And if you just leave that pure ratio, if you just literally leave it and don't convert anything, then what you're left with is called radians. If you then decide to divide the whole circle into 360 parts, you could call each one of them a degree, and then everybody gets used to that and everybody's happy. But that doesn't actually add, that only complicates things further. What we're going to say here is we're not going to divide the circle into 360 parts or anything like that. We're just going to say the measurement of an angle is the pure ratio of arc length to radius. That and the unit for that idea, or not the fake unit for that idea, is called a radian. So we're going to say, for example, when you go around an entire circle, the circumference of an entire circle is 2 pi times the radius, right? No matter how big a circle you have, like that's the whole nature of pi. So if you go around an entire circle, the ratio of circumference to radius, like all the meters that you took going all around divided by the radius straight across, that's 2 pi. 2 pi is the number of radians that comprises an entire circle, just by this definition, okay? Like again, you can call that 360 degrees, but that involves introducing an extra step that we all think is easy only because we're really used to it from childhood. But if I don't introduce that extra step of 360, I'm just saying that to go around an entire circle is 2 pi radians. When I say that, what I mean is, I don't care. I mean, this is the nature of pi, is that you pick any tree in the forest, cut the tree straight across, put a string that represents like literally, I mean, this is what pi means. It means go to any tree in the forest, cut the tree in half. So now you have like a cross-sectional circle, like the tree trunk is like this. Go across that tree trunk, like mark it with a string or with a ruler, see how far it is straight across. Now take a piece of string and go around the whole trunk, right? I know this sounds stupid, but let's just get this straight, what this whole pi mysticism is all about. If you go around the whole tree with a string and you lay the string down, and then you take another string where you just went straight across the tree, put the 2 strings next to each other, and you'll find that going around the whole tree always is a tiny bit greater than 3 times as long as going straight across. This is what pi means, right? I mean, that the circumference of a circle is always pi times greater than its diameter. Going straight across is always the most efficient thing. Going all the way around is always 3 times less efficient. That's true no matter what size the tree is. That's why pi is a constant. The ratio of circumference to radius is always just about 3. Therefore, the ratio of circumference to radius is always just about 6, right? Like 2 times pi, like 3.14 times 2. So like 6.28, whatever. That's a little more than 6. So I'm saying now, I'm really trying to say something here, believe it or not. I'm saying, like if your brain fogs the minute you see the word radian, and please admit to yourself if it does, and mine did until I was 35 years old, like seriously, if radians come into our discussion, please admit to yourself if the minute the radians come in, it's doing a shutdown thing in your brain somewhere. It would be totally fair if that were true, but I want to like get you out of that now. So the only way to get us out of that is to admit that it might sometimes happen. If you've ever been sort of like fogging your way through radians or trig, or kind of, like just white knuckling your way through, I'm here to tell you that what a radian is ultimately, well, what any angle is a section, a fraction of a circle. And what a radian is, if you really think about it, is a 1/6 of a circle. And that's all it is. A radian is approximately, but always just about a 1/6 of a circle. That's what and here, in fact, yeah. So I'm saying, like, there's precisely 2 pi radians to a full circle, okay? And this is all related to us. We care about all this mathy, circly stuff because here we are in physics watching some behavior that is cycling. So from here on in, we're going to start saying, oh, in any given circle, there are 2 pi radians. What's a radian? A radian is a 1/6 of a circle. it's technically it's 6.28 of a circle, but so each radian is just about 60 degrees. I'm going to show you a picture of that in a second. But 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 there's like 6 of them in every circle. Therefore, from here on in, if we're going to look at anything that cycles, we're going to divide cycles into little portions that seem odd, but come from our knowledge of circles, because we have so much mathematical power to analyze and predict things in circles, that from here on in, anything that cycles, we're going to treat anything cyclical as circular in effect. And we're going to say every time I see a cycle, whether it's in the washing machine or in an oscillator or like in an electrical system, anytime I see anything that cycles, I'm going to think from now on, and I'm going to think every cycle is 2 pi radians. A radian is a sixth of a cycle. Like more specifically, like here, if this is as clear as I can make it, like if you think about it, if angle by definition is arc length per radius, if that's what an angle of any kind is, a pure fraction, it's just a way of us. So again, what's a 90-degree angle? It's really a half of a circle. What do I call that in this new language? I call it pi over 2 radians. Why? What do I mean? A radian is a sixth of a circle. So there's about 1.5 of them to 90 degrees, right? That didn't help anybody, I'm sure. But like, remember, an angle is, so different way of saying it now, an angle is arc length per radius, like this thing right up here, arc length per radius. So an angle will be precisely 1 radian as long as, like, if the arc length is equal to the radius, right? This is where I'm going with this. If you really get what I'm saying, that angle is just arc, and I know you've heard it a million times before, but so had I, and it never meant anything to me until it did. If an angle is arc length per radius, then just imagine a situation where the arc length that you sweep out is precisely equal to the radius. Like, again, we're saying that to go around a whole circle, you have to go 6 times. You have to go 6 radii to go around a whole circle. Always. That's the nature of a circle. A whole circle is 2 pi times as great as a radius. So to go around a whole circle, you usually have to go a little more than 6 times the length of the radius of that circle. I'm saying, what if you make them equal? If you make S equal to R, then S over R equals 1. That would be what 1 radian is. What is 1 radian? 1 radian is that section of the circle here drawn in blue, for which the S, like the subtended arc length or whatever, the arc length is literally in meters equal to the radius. In other words, what I'm really saying, now I'm going to drum this in like even more. Again, from now on in life, like everybody thinks they know degrees and everybody thinks they don't know radians. I'm here to say you know degrees just because you're used to them from childhood. The idea that we divide a circle into 360 parts is not actually something that anybody can possibly be claiming makes sense to them, because like it doesn't. I mean, there's a reason for it, I can explain. But there's no way when you look at some snowboarder twirling in the sky and you go, he did a 360, there's no way you're thinking, oh yeah, that makes sense because he did a full circle and we divide the circle into 360 parts, because after all, it does take the earth, like the big circle that the sun makes around the earth or the earth makes around the sun. Actually, if we divide that into little sections, called each one of which the amount of time that the earth takes to go around itself, there's about 360 of these in one of those. So, oh, I guess it makes sense that the circle I'm drawing on a piece of paper, someone just divided into 360 parts. Let me tell you, that is the reason, okay? It actually is the reason. And actually, in my mind, it is beautiful. It's totally cosmic and wonderful to me that circles on the ground are divided into 360 out of reverence or application to the big circle in the sky that's divided by 360. But heck, that does not help us do the math at all. And I don't think any one of us is thinking that when we're doing degrees, right? But that is historically where degrees come from. They're not actually helpful, is what I'm trying to say. They're interesting, but they don't make things easier. It's easier to divide the circle into small sections like this, into fewer number of bigger sections like this, and to realize that a radian, if you really want to get down to it, what a radian is the slice of pizza that comes closest, and I'm going to say this, I want to make sure everybody is, what a radian really is the slice of pizza that comes closest to looking like an equilateral triangle. for any pie you picture. I mean, any pizza pie you picture. I'm saying if you really get what a radian is, then you're getting that I'm saying that a radian is that angle, that portion of a circle for which the edge is literally equal to the crust. Now the crust is always round, so it's hard to see with your eye. Like it's hard, you can't construct a literal equilateral triangle, with a round side, right? But you can make a thing where the round side is equal in length to either of the two straight sides. So it won't look perfect to your eye, but I'm saying picture any pizza you want. Picture dividing that pizza like evenly so that each person gets a slice that basically looks like an equilateral triangle. In other words, each person's going to get a very squat slice, like not a long thin slice. A long thin slice is never 1 radian. That is way too small of an angle. It's like a couple of degrees. A slice that is a radian is a slice that literally looks like an equilateral triangle as best it can, given like a curvy crust. Right? That is what a radian is. It will always look that way. It's like a sixth of a circle plunked out, because around the whole circle is like 6 times. In other words, so it's not exactly right. I mean, so if you call the whole circle 360 degrees, then a radian is a little bit shy of 60 degrees. It's like 57, okay, which I know you've heard in math before, but I'm trying to say, so you do want to picture, like that is a radian. That, and it doesn't have to be measured in pi numbers or anything. You can have 1 radian. You can, if you have 2 radians, then that's like almost 120 degrees. That's what a radian is. So from now on, so what is a radian? So what a radian is, yeah, it's an equilateral pizza slice. What's that got to do with masses on springs? A radian is a sixth of a cycle, a sixth of a cycle. Therefore, when we talk about omega now, this omega that all we knew about it was that it was radians per second. That's all we originally said. Omega has to be something measured in radians per second. Now what I'm telling you is, well, a radian is a sixth of a cycle. Omega is measuring how rapidly this system is cycling. It literally is measuring, in effect, cycles per second, only it's off by a factor of 6, if you like. It's like if you were to just watch your mass on a spring go back and forth, back in the lab or in a simulated COVID-friendly lab, and you watch your mass go back and forth. So imagine counting like how many times it makes a full round trip per second. If you counted the number of times it does a full round trip per second, if you multiplied that by 6, you'd have omega, because omega will tick every time this thing does a sixth of a round trip. Of course, we would all prefer to count full round trips, but the math, because of the way the math is working, the math is a tick counter that's going every sixth of a cycle. So it's totally conceptually the same, but it's like there's a unit conversion going on. And we are physicists. We do want to live in the world, and we do want to be able to relate to what we're talking about. So we can rewrite this or re-understand this omega. So again, this is everything I'm saying here, by the way. I'm sorry. I said finding number one, like I said, like on page 5, actually, I said finding number 1 that we have so far is that if d2x dt squared equals negative k over mx, like if we have Hooke's law, if we have a mass on a spring of certain stiffness, what we're saying so far is we could just look at that system and right away say it's going to oscillate at a constant angular frequency of omega. And by angular frequency, we mean a measurement of radians per second, which what I'm trying to explain here means we're counting cycles per second, but every sixth of a cycle. So this is all still under finding number 1. Finding number 1 is what we can learn about the cycling rate of an oscillator, just based on its original measured information. So now I'm saying angular frequency is weird. Omega is what the math allowed for us, but it is weird. It's counting sixths of a cycle. You don't want to do that. I don't want to do that either. Or, it's counting cycles divided by 2 pi, if you like. So we can certainly take that. So say someone looks at our mass going back and forth on a spring and says, oh my God, or that thing is going fast, or they do a calculation. And they say, oh, that thing is doing like 6.28 radians every second. it would be perfectly reasonable for us to go, wait, it's doing 6.28 radians every second. You mean it's doing like 2 pi radians every second. So you're saying it's doing a full cycle every second. That's what you're saying? Like, oh, well, that's an easier way to talk about it. Once the math spits out omega, we can certainly use a little math to turn omega into a number that we can relate to more. In other words, I'm saying from now on, lowercase f, this doesn't mean friction now. This is a new letter I'm introducing with a triple equal sign. Like lowercase f from now on will stand for standard frequency. Standard frequency, the kind of frequency that we could all maybe relate to and we would care about if it weren't for exotic mathematics, right? Like how many times does Yaverbaum say the word like every lecture? Oh my God, per lecture, he says the word like 43 times. Okay, so the frequency of likes per lecture, oh, that sounds good, but the frequency of that word usage per lecture, 43 times. Wait, horrible example. Let me start all over again. Let's say I use the word like 3 times every second. Okay. If I cycle through using the word like every second and we measure that, that's measuring a standard frequency. No radians, no circles involved, straight up just how many cycles per second. In fact, it's such, and this is a standard way of measuring things. This is an important concept. This concept of standard frequency, this is like the equivalent of velocity for any system in the world that's cycling, right? It doesn't matter what the size of a cycle is, doesn't matter what type of cycle. It could be an English cycle, it could be a washing machine cycle, electrical cycle, spring mechanical cycle. As long as something is repeating its behavior over and over again, the easiest way to describe it and identify it is how many times does it repeat its behavior per second. One such thing, one cycle per second is called a hertz. Okay, like it's like the guy's name, like the rental car company's name. Unfortunate name because it ends with a Z, so it makes it sound like it's plural, but it's not plural. 1 hertz is 1 cycle per second. So if you have many hertz, it's like sheep or fish or something, like 1 sheep, many sheep. Like, sorry, life, English, I don't know what to say. But so 1 hertz is 1 cycle per second. Literally, then 1 hertz equals 2 pi radians per second, right? I mean, that's a conversion factor here. And this is all important because we're now dealing with cyclical systems now. We have to think about units here, but it's also a little bit tricky because bear in mind, like a cycle is a thing and it's a word that I'm using, like 1 hertz is 1 cycle per second, but a cycle is not a standard unit of MKS. Like a cycle is not a meter or a kilogram or what's the other thing, or a second. A cycle, because a cycle is just, a count. It's a pure number. How many times did Yaverbaum do that thing? And the thing that he's doing might not be measurable in meters or anything else. So a cycle is just a word that we write down. It's actually, here, what I'm trying to say is, okay, this is inexcusable. I might have to write this again on the next page. What I'm saying though, I'm saying that, so omega measures radians per second. We can, which is hard to relate to, but it's mathematically direct. I mean, that's why I'm talking about it so much. Like omega is something that pops out of the math. It's there because we're looking at cyclical systems and we're choosing to use our mathematical knowledge of circles in order to analyze the cyclical systems. So omega comes out, so radians directly come out of the math. Then we step back and we say to ourselves, okay, that's what the math is doing, and we need that. And whenever we're doing the math, we're going to stick with omega. But if we're really trying to picture in our head what we're talking about, like we tend to convert angular frequency into standard frequency and just talk about cycles per second. Now, this works. Please understand, in both cases, neither a radian nor a cycle is actually a unit. They're just a word that we're writing there to hold a place in all of our unit analysis. Technically, both radians and cycles are dimensionless. I mean, that's why we can go back and forth between them. There's just one just happens to be 2 pi the size of the other. A hertz, a cycle per second, is the thing that sort of in the real world people relate to. And so just one quick example of that, just to make it more like, if you listen to NPR or, you know, a radio station, like NPR is, and I'm not, this is not an advertisement, obviously, but like, because I keep forgetting that. Oh, or what, 105.9, which I guess is what I listened to when I grew up here. Like 10, and I don't know if it's the same kind of music anymore or not, but 105.9 megahertz on your FM dial means something similar to 93.9 megahertz on your FM dial when they say broadcasting from the top of the Empire State Building, blah, blah, better than the internet any day. Like what there's a megahertz, mega means million and hertz means cycle per second. So when they tell you that their radio station is 93.9 megahertz, they are saying that something is oscillating, cycling, making a round trip of some kind, going back, undergoing some certain periodic behavior, back and forth, 93.9 million times per second. And that is true, by the way. They are saying that, and it is true. And the thing that is vibrating back and forth 93.9 million times per second is an electromagnetic field, which is the punchline of this class. Like, we're totally going to get to that. Like, that's where this is all building at, to tell you the truth. It will take us a little while to get there to explain fully what we mean by electromagnetic radiation, but electric fields and magnetic fields, which is the thing we need to learn, those are the things that are traveling from a radio transmitter to your radio receiver antenna, if anybody ever does listen to the radio anymore, which I don't even know. And those fields are oscillating in strength. I mean, I'm getting ahead of myself here, but just so you, like, the thing that's vibrating at 93.9 or oscillating at 93.9 million times per second is an actual real thing for sure, but it's not a distance in space. There's no object going there and back 93.9 million times. What's happening is the strength, the magnitude of a certain vector, of something we call the electric field vector, sort of the strength of an electrostatic force that's kind of waiting to happen, is going up and down in magnitude 93.9 million times per second. Like, it's even more abstract than this is, but it's all connected to the same thread, that hertz are hertz are cycles per second. They are ultimately related by means of 2 pi to radians per second. But then we can go one step further and make it even more real, hopefully, and say, oh, actually, the thing that's the easiest to relate to, I mean, we can go one step further to this page and say, oh, actually, the thing that's easiest to relate to physically, in fact, the thing that's most available for us to observe and, measure, is the thing that we measure in the labs. Like, notice for 2 weeks, you're talking about, or whatever number of weeks in this crazy class, like, you're looking at springs in your so-called lab, and I know that's challenging to say the least. But you didn't measure any radians ever. Like you were asked to make a radian measurement, and you couldn't have, because the mass is going back and forth and back and forth. You wouldn't, if you were asked you to find radians in that straight line, you'd rightfully be like, what radians? You didn't even measure hertz. What you measured is the thing that is most logical and easy to measure and picture. You measured period, right? At least in one lab. You talk about period. Period is the reciprocal of frequency, right? Of standard frequency. If standard frequency is cycles per second, then period is seconds per cycle. It's literally the flip, right? Like, if I run 4 laps around the track per hour, then that means it takes me 1/4 of an hour to run a lap. Right. So one is cycles per second, the other is seconds per cycle. In both cases, the cycle is like not actually a legitimate unit. It's just sort of there. But so from now on, capital T, from here on, I know you've already been using it in lab, but in lecture wise, from now on, even though lowercase t still for all time means the variable time, capital T now refers to, in any given context, a constant, a specific number. Capital T is the specific amount of time that one cycle of any kind of oscillating behavior undergoes. I said that clunkily, but so now what I'm saying in sum, this is a lot of verb. I'm actually ultimately, if you're following this, I'm saying we have three independent, equivalent ways to identify an oscillator, three equivalent ways to convey the one key piece of information that will characterize any given oscillator. Any given oscillator does the same thing over and over and over and over again. While all conventional types of motion are in perpetual flux, right? Let me say that again. Like, why we're spending, I mean, oscillators are fascinating systems, or they're very important systems, because if you go back, like, and that's why we're taking so long on homework 1. If you look at all the preliminary questions of homework 1, like not question 9 yet, what they're all trying to get across is like anytime you try to identify something about an oscillator that seems constant or reliable or dependable, particularly any of our old quantities that we used to use in physics to rely on as constant or reliable or predictable. If you look at position, if you look at velocity, if you look at acceleration, each one of the force, each one of these things is continuously changing in an oscillator. That's what's sort of confusing. Like, the velocity is always changing, the acceleration is always changing, the jerk is always changing. Every single derivative, every way of describing motion is in perpetual, smooth, continuous change in an oscillator. Yet something about it is steady. It's what it is. What's steady about it is that it's oscillating. If we could nail down that rate, the rate of oscillation, that's the characteristic identifier of an oscillator. And what I'm taking all these pains to say is there's three different ways to express that one name tag. Like, the name tag for an oscillator is the rate at which it's oscillating. There are three equivalent ways to nail that down. You could talk about its omega, angular frequency, or you could talk about its F, its standard frequency, or you could talk about it T, its period. They all literally convey the same information. Like literally, like if you have one, you automatically have the other two. And that's important. Like, any one of them gets you the other two. But the reason we have, and again, let me say that again, any one, so if I ever on an exam or something like this, like if I give you any one of those pieces of information to describe any kind of oscillating anything, please write it like you want to know in your mind. It's a lock. Those three are lock. If you know one, you automatically get the other two. Omega gets you F when you divide by 2 pi, and F gets you T if you flip, if you reciprocate, and you can go around the mulberry bush in any direction. So of course so I'm really trying to emphasize all three of these are equivalent. If I expect that we can be flexible between the three of them, but you would maybe very reasonably ask, well, Yaverbaum, for God's sakes, first of all, can we get into word and edgewise here? But second of all, if really the three are totally that equivalent, if they're literally equivalent, why do you physicists have to jam up our lives and like make all three of them? If they're equivalent, isn't that like super redundant and annoying and just confusing and typical physics? Like, it seems that way, but no, the reason we have all three, I mean, totally fair question that someone might be asking, but the reason we have all three is because all three come up. Well, I'm trying to warn us that we should be able to navigate between the three, but the reason that three come up, well, it's exactly what it says on the sheet. One directly comes from the math and is by far the easiest thing to use and to stay with when you're doing the math, i.e. when you're analyzing your data or any of your conclusions about any kind of oscillator. That's omega. Omega is what's coming from the math. If it seems a little bit abstract or like not like physically realistic to you, you're not alone. You're right. It's coming from the math. In math land, we like to think of sixths of circles and pi and all that stuff. But T, on the other end of the spectrum, capital T, is coming directly from the empirical world of data, of our 5 senses, of what you can actually measure in the lab. In other words, T is the most scientifically accessible quantity and probably the one that we can picture the most easily, observe, and care about. But omega is the one we can work with in the math. And the bridge between the two is F, standard frequency. So basically, if you're in a theoretical context, you got to know how to navigate omega. If you're getting your lab straight up from measurement, you gotta think T. The way to cross between the two is F. That's the point of this part of the list. That's all. I'm gonna take a breath for a second, really. But everything I just said is trying to kind of flesh out or support finding number one of this homework or of this unit. Finding number one, which was written on page 5, I think. Yeah, just to remind you, okay? And then, of course, we're going to pause and there aren't a million findings for today. There are 2 findings for today, and it's 4:05. So yeah, okay. So just to remind you what I'm saying, finding number one is very specific. I mean, it may not say, well, it's comparatively specific. Finding number one says, if you're walking in the forest and you come across a mass of M on a spring of K, very strange forest, granted, but you're just like walking, or someone presents you, here's a mass of M, and it's on a spring of K, and they're like fixed to the wall, no tricks up our sleeve. Finding number one says they can release that mass from any position now. They can release that mass from any position other than the equilibrium, and it'll start oscillating back and forth. And you can know, you'll know right away that that's going to happen. And you'll know right away, just looking at their mass and looking at their K, regardless of where they put their mass, where they release it from, you'll be able to say right away, aha, that mass will oscillate back and forth at a constant rate of square root of stiffness over mass. Like the finding number one is sorry, finding number one, I'm going to write it again. Actually, I'm going to wait, let me insert a page. Sorry. I just want to make this as clear as I can. If I'm going to call it finding. Okay, so in math terms, like finding number one is given spring of K, mass of M. In other words, and given Hooke's law, right? Given what Hooke's law tells us about mass on a spring, then the mass will obey this equation of motion, will oscillate cosinusoidally at a certain rate, and the rate is the square root of the spring's stiffness over the spring's mass, right? That's the finding. And you might even say, well, didn't we know that 3 days ago? Like, why? Like, that seems like the whole finding of the whole class. Like, I mean, partly what I'm really trying to emphasize about this finding number one is note that omega, that when we say we solved for omega and we got the omega squared of K over M, first of all, yes, it's nice that we have an expression for omega. That is a finding. Like I could have said omega is, square root of K over G, like whatever I found, if I found what omega is, that's cool. But now let's be more specific about what we found about omega. We found that omega is entirely determined on K and M, as opposed to, like, it's not determined by, it's not dependent on, like, I'm saying, we found this. There's no X naught term on the right-hand side of this equation. If we're saying K and M are constants, but I'm going to give them a new name. I think I have not used this name yet. I'm going to say K and M are a very special kind of constant. Like there's lots of different kind of constants in the world. There's Planck's constant. There's the universal gravitational constant. There's the permittivity of free space constant. These are not those kind of constants, K and M. They're not like universal constants or something like that. They're constants because they represent measurements that we made of the materials that we use in our system here in the physics system. They are not going to change throughout the behavior of our system because we believe they represent constant material properties of our system. And we call such constants parameters. Parameters, again, are material properties of a system, like measurements you make of the actual objects, ingredients that you're using in whatever physics experiment you do. So a parameter can differ. In other words, K can differ from one spring to the next. Not all, so it's not constant like in the universe. K is not a constant in the universe. It's constant for a given spring. You make a measurement of that spring. It now has that K. Now you set it up in an experiment and you assume or you believe that the K will not change throughout that experiment. What we're really specifically saying here, therefore, why this finding one thing is kind of a big deal is we're saying that in this expression, x equals x naught cosine omega t, we're saying that omega thing that we've now solved for, we're saying like omega, we knew the minute we looked at the spring system, like before you set it up, before you dragged your mass back to 0.15 meters or whatever and let it go, just when it was sitting there, we looked at it and we said, oh, that's how stiff that, I mean, I'm saying now, like according to these equations, evidently, we could just look at a spring system and say, oh, it's that strong. Oh, it's that massive. Oh, then when you pull it back, it's going to oscillate at this rate. It's going to make like 3 cycles per second once you pull it back. We could say that looking at the mass springs and now hear this. I mean, I know I've said this once before, but this is really such a big deal to me. So you're holding your mass on your spring, like you're in a lab or you're in a virtual lab, and I just like pop into your Zoom room unannounced and you didn't have a password. And so I say, what are you doing? And you say, well, look, I've got this mass on this. I'm having a great time. I've got this spring here and I got a mass on one end and the other end of the spring is like hooked to the wall. So look how heavy my mass is and look how stiff my spring is. This is going to be, in a minute, I'm going to pull this mass back and let it go. And it's going to oscillate. And I'll be like, yeah. When you pull it back, it's going to oscillate at exactly this rate, like square root of K over M. And you say, whoa, wait. Don't get so cocky. I mean, I haven't pulled it back yet. Like maybe I'm going to pull it back to here to 0.15 meters, but you don't know, Yaverbaum. I could instead decide to pull it all the way to here to like 40 centimeters. And what I'm saying is, well, I don't care. I don't care where you pull it out to. Like my math says that omega is a function of K and M, these parameters that you measured before the system you started. Omega is not a function of x naught. I don't care where you, apparently it doesn't matter where you pull it back to. It's still going to cycle at the same rate. It's entirely determined by the system ingredients, not the system configuration. Again, I know maybe I've said this once before, but maybe it's a little bit more of a vivid thing to see now. I'm saying that you can pull your mass back to 15 centimeters and it'll go, there, back. Or you can pull it way out to 35 centimeters. And you can say to me, well, now what you going to do? Because now this thing has to travel all the way 35 centimeters and all the way 35, but like it's a much longer trip now, Yaverbaum. So before, when it was at 15 centimeters, it went like four times a second. Now pulling it all out here, you think it's going to do 4 times a second again? No way. It's got much farther to go, you might say. But even though it's got much farther to go now, and I'm really tempted and stop and ask you guys what my next sentence is, but I'm also really nervous about the time. If anybody sees where this is going, feel free to put it in the chat or whatever. I'm not going to stop for too long because I know but I'm saying again, like what I'm trying to say here, is if you're following this omega discussion, it seems that omega is a cycling rate. In your mind, just think of it as omega really is interchangeable with F. It just means frequency. It's just like always off by a factor of 6. But if you're just picturing in your mind, we're saying the rate at which this thing goes back and forth has nothing to do with how far back you initially hold it. If you pull it back to 15, it's going to make short distance oscillations. If you pull it all the way back to 35 centimeters, it's going to make much greater, farther, more distant, spatially huger oscillations, which I would think would affect the time. but it doesn't. Because evidently, if I pull the thing back farther, as we saw in questions 4 and 5, if you pull the thing back farther, you're giving it more and more potential energy to the whole system. When you let it go, it's going to eventually convert that potential energy to kinetic energy when it gets to the center. So anything that you pull back more has a lot more kinetic energy when it gets to this equilibrium position than something you didn't pull back a lot, right? So on average, the thing that you pull back more goes faster, maybe obvious, maybe not. But this whole package is definitely not obvious. I'm saying the masses that we pull back farther, they start farther away from equilibrium. They have much farther to go, but they also have more potential energy. And by Jove, strangely, the exact extra that we're asking them to go turns out to be exactly compensated for by the extra speed that they get having all this potential energy out there. Now, that is also not, that is a surprise. That is not obvious because like kinetic energy is 1/2 mv squared, potential is 1/2 kx squared. Like, why would one perfectly compensate for that? But it does. The farther back you hold this thing, the faster it will go on average through its round trip, its cycles. Therefore, thereby, we end up with a situation where no matter where you pull it back to, the rate in time will be a constant called omega. That's like and that's what we really mean by harmonic, that this omega is not affected by x naught, that the rate of cycling is affected only by material parameters, by system ingredients, not by system configuration. So I'll say it one more time. Oh God, is it? Okay, hold on a second. So we're just about to wrap up. I'm sorry. Okay, I'm saying and we definitely have to go now. And I'm sorry, this is just to sum up finding one. I'm saying finding one mathematically is d2x dt squared equals negative k over mx, means x equals x naught cosine omega t, omega equals square root of k over m. Like the three equations put together, in effect, is what I mean by finding one. But what I'm saying in English is finding one tells us that if you have a mass on a spring and you let it oscillate, it will oscillate at the same rate in time, no matter how you set it up in space. I.e., a mass on a spring system is the fundamental essence of a clock. It keeps time irrespective of space, right? That is the true word for that in physics is a harmonic oscillator. The fact that this thing's angular frequency, its cycling rate, depends on ingredients, not on conditions. It doesn't matter how you set it up, it just matters what you set up. The fact that it keeps time that way is what we mean by harmonic oscillation, that the angular frequency remains constant, independent of amplitude. That's finding number one. I think we've won. Finding number two is simply this. is that everything we just said about X's and K's and M's, everything we just said, we learned it by doing math. And the math doesn't care if you call it K or M or X. The math doesn't care if we actually literally have a metal coil on a block or not. In other words, finding two, and this is where we're ending today, but finding two is just writing this exact same thing down. Sorry, oh my God, where did finding two? Finding two, did I lose it? Well, I'm gonna finding two is this. I don't know where it went, but finding two is this. And if you have to go, I'm going to tell you right now, I'm just going to write the exact same thing that we just wrote with X's, but I'm going to write it with Z's instead. And that's finding two, because finding two says this is true for any dependent variable measurement you could ever conceive of in the world. Anything that you could ever measure doesn't have to be space, doesn't have to be on a metal spring. Finding two, and this is where we're ending. I'm sorry, I'll just write it. Finding two is all I'm doing is changing the X's to Z's, and I'm getting rid of the K's and M's forever. I'm saying from now on, if there's anything that any quantity that you measure, and you have reason to believe that that measurable quantity, that dependent variable, could be distance from a position, it could be angular distance from a position, like as in a pendulum, it could be electrical field, like in a circuit, or it could be temperature, like in homework 3, anything. Oh, and this is key for homework 3, what I'm saying right here, and homework 2, whatever, any measurement you ever make, call it Z, any measurement at all. If this differential equation applies to that measurement, if this differential equation is true for any reason that you have to believe, then the solution to it is the solution we just found with X's. In other words, all the math we just did with X's will work on any letter. Therefore, we don't have to know in advance that our system involves a spring or distances or anything. As long as something we're measuring satisfies this differential equation, then the thing we're measuring is oscillating harmonically in time with an angular frequency that is the square root of whatever that constant is. Like whatever's in parentheses, the square root of it is the angular frequency at which that value will oscillate. That's the conclusion. I know it's totally late and the other class is coming and you have to go. So I'm just going to thank you very much for your patience. Sorry, just keep doing what I'm going to say goodbye if anybody, sorry. But thank you. Thank you guys very much. Sorry to, okay. I'm literally ending. Thank you.